everyone. Thanks for attending my talk. I know it's a remote presentation, but I hope you can still get the key idea of our work. So the talk title is CloudLeak, DNN model extraction from commercial MLaaS platform. So the presentation should be provided by me, my students Honggang, and my collaborator Tsung-Yi. But due to all the technical issue and the recent situation, I will be the person who gives the main presentation. So first, myself, I'm Yier, an associate professor and an IoT term professor at the University of Florida. So I think you know a lot of hackers. You may not be that familiar to professors, so I list my research interests. I'm also using this opportunity to recruit students if you want to do PhD or master in this area, cybersecurity area. And we are also interested in IoT and CPS security, as well as hardware security. My collaborator, Tsung-Yi, he's a professor in the Department of Computer Science in National Tsinghua University in Taiwan. So he's also the program director of Taiwan's Ministry of Science of Technology's AI Innovation Program. That's why we are working on AI. Luckily, we are not our collaboration turned out to be very productive. So I hope we will continue this collaboration. And the third speaker is Honggang. I will let him introduce himself.
Good morning. Welcome to my talk. My name is Honggang, and I am currently a visiting PhD student working with Dr. Yier. My main focus is on the machine learning security, and besides, I also doing some research such as on the embedded system security, IoT security, and the machine learning computing system design. Today, I'm going to talk about the adversary example-based model stealing attack. And now, my advisor, Dr. Yier, will give you the full talk.
Okay, so these are all the speakers. So let me quickly give you an outline of what we will discuss. So I assume that many of you already know AI and AI security adversary example, for example. So that's why I would quickly go over this background, and then I would introduce you how the model extraction attack can be applied to those commercial platforms. In Microsoft, in Face++, in IBM, in Google, in Clarifai, all these platforms. So we will also discuss the potential defense. So first, deep neural network has been quite popular these days, and it's become deeper and deeper. So in the original implementation, we have one layer, then we have multi-layer, and now we have deep convolutional network, neural network. The neural network is nothing new. It's been there for decades. But until recently, they seem achieved a great success in all different areas, such as voice recognition, image recognition. And one main reason is that using the DNN, we're using more resource so that we can get better classification results. And as a result, we can see that the parameters of a typical DNN structure also increase from several thousand to tens of millions. So this has also become one challenging that in our work, if you want to steal a DNN model, you need to recover millions of parameters. It was deemed impossible. So I would show you how we make it possible. So before that, let's take a look at the application of commercialized deep neural network. Okay, So we have mainly two parts of them in two different markets. One is we call the machine learning as a service. So it's mainly deployed in the cloud platform. We're using a lot of resource. And the other is more or less in the like cell phone. So it's become, we are using TensorFlow Lite. And these are all different areas. So we use them on the cloud, we're using them on the cell phone. So what we are focusing on in our work is mainly focusing on the machine learning as a service. So what is machine learning as a service? The idea is that someone as a supplier, they have a data set. So they're using a training API, which is provided by cloud. Instead of train locally, they rely on cloud resource. So the cloud resource would provide the training API, and the supplier would put their data set inside and do all the training. And eventually, after the model has been trained, the cloud will provide a prediction API for users. So user would put in a picture, for example, they want to recognize a flower, what type of flower this is. So they give this flower. If you like fishing, you will give a fish picture. And for each query, they will charge you some money. So we know that for the data set, original data set is normally sensitive data. And for the machine learning model, it's a black box. So eventually, for this machine learning as a service, they want to achieve two goals. First, they can provide a very rich prediction API. Second, they can provide model confidentiality. So this is the key idea of the machine learning as a service. And it's become very popular because the machine learning as a service model can save the local computation resource. You don't need to buy these expensive DNN servers, right? That's why almost all the cloud providers, they have their service, machine learning as a service. For example, we list Microsoft, Face++, IBM, Google, Clarifai, all of them. And some of them provide a general purpose machine learning model. Some of them provide a dedicated machine learning model. For example, the Clarifai, their product is not safe for work. They are screening images that whether you can view them at work or not. Some of them allow you to customize them. Some of them already customize everything for you. But all of them are using black box, using neural network as the model, and they also monetize them, which means that you need to pay for the service. I want to emphasize one thing is that almost all these services provide you a confidence score. It's actually very important for you to extract the model. But in our attack, we can eliminate the use of confidence score, which means that we can rebuild the confidence score. So that's, again, something we will emphasize later. So this is a black hat. I think everyone is thinking something that whether I can hack something. Now we have machine learning as a service. People are thinking that, okay, how can I hack it? So one typical hacking is we call the model extraction or model stealing attack. So the key idea is that, okay, you put a model as a black box in the cloud, and the model will generate money because everyone will query it and get the result. But if I can steal the model, then I can put the model in another cloud service. Other people, other users would using my model and pay for that. So if I can extract the model, then I don't need to go through the data set collection process. I don't need to pay for the machine learning as a service, the cloud service, a lot of money to train the model for me. Okay, so you are not alone. People already started working on that in the last decade. Here, just a list of 4 interesting papers that some of them would provide you high accuracy of the extraction model. But if you look into this table, you would realize that if they want to extract the machine learning model with a large parameter size, hundreds of million parameters, their query will be also very high. So with a high query, for example, they needed to 100,000 times to query the model. Then the cost will be also very high, which means that as a hacker, if you needed to spend a lot of money in order to extract the model, then you would ask the question, did it really worth it? Because with that amount of money, you can train the model by yourself. Okay? So still an unanswered question is that possible that take a very few query so that to reconstruct a model? And the HNCCS 2017 paper give you an answer, but this answer is not perfect because they only using 7,000 query, but the reconstructed model have very low accuracy. If that's the case, then no one would use it. Okay, so for a while, people believe that this is something that is not easy or does not worth it if you query that many times. And we look into the same area, but we look into the same area from a different angle. So now I want to introduce you another machine learning attack, adversary example. For those no adversary example, you would thinking that what's the linking between model extraction and adversary example? For those who may not know the adversary example, I have a quick example for you here. So the adversary example is trying to leverage the machine learning model's intrinsic vulnerability. That is, you have one image. The machine learning model would successfully classified as, for example, in this is a panda, right? But if you add in some perturbation, it's more like random noise from our raw eye. So you generate another picture, is the third panda image there. But now, if you give this image to the machine learning model, they may tell you that it's a dog or something else. So this is adversary example. And the moment people notice that, in fact, the adversary example is way more popular than model extraction attack. So people come up with all different solutions. I mainly divided them into non-feature based or feature based. Again, it's only my kind of like a category. So here are some examples of C and W attack. You have the source image. You're trying to include some perturbation, and you have the adversary image. So the left figure, 0 and the plane is the source image. And the right, all three figure are the adversary image. So that if you ask the machine learning model to tell you what they are, they will tell you this number could be 1, could be 2, could be 7. The plane could be anything else. So, and we also have feature-based. So the idea is that you have a source image, and you also have a guide image. The key idea is that the perturbation would be carefully designed so that the source image plus the perturbation will become the guide image. So for example, the left bottom 4 figures, the adversary example, the pie will be recognized as another small animal here. So this is the key idea. So okay, now the point is that what is adversary example from mathematical background? I sometimes love to investigate or study the mathematical background. I know many of you using AI, your job is just to adjust the parameters. Why bother the underlying math, right? Why we do AI is because we don't want to do math, that's why we do AI. AI will provide the magic to solve all the problems for us. So we don't need to learn the math. But my focus is that, okay, what is the math background of the adversary example? So here is a simple view, step by step. Let me show you what is a simplified view of adversary example. So first, you normally have a source example, the source image. The source image is to the right of the bar, assuming that the bar is the boundary of the machine learning model. So you would generate, when you're adding perturbation, you would generate a lot of examples. And this green circle is still a legitimate example, which means that the perturbation is not large enough so that the classification is still correct. But the dark green circle is a bit tricky. The perturbation is large enough, very large, but still not large enough to flip the classification result. But the confidence score is already very low. And to go further, the red triangle is the perfect adversary example. They have high confidence, but the classification result are wrong or incorrect. Okay? So in normal adversary example, we are trying to build this red triangle so that to fool the system. But in our case, we realize that what is the really useful example for us is those gray triangle and the dark green circle. These are very close to the boundary. Sometimes they are classified correctly, sometimes they are classified wrongly, but they all share the same property that this classification will give you very low confidence. So we notice that if an adversary example with very low confidence, then the adversary example is likely close to the boundary. That's why the classification would give you very low confidence. So what we are doing is that if we don't need to generate all this example, but we only generate a low confidence example so that we can quickly recover the boundary. Eventually, what we want to recover is the boundary because the boundary defines the model. Okay, so now you see the two links that with the you leveraging the adversary example, we may be able to extract the boundary at a very low cost. Because we're only using, instead of using randomly generated queries, we're only using this low confidence, either legitimate example or adversary example to query the black box model to identify the boundary. So now another simple question comes. How to generate these boundary cases with minimum confidence? So we can leverage all existing solutions, like all this adversary example method can be leveraged. In fact, we come up with a new solution, just one on top of that, we call the feature full. So this is more like a dedicated solution to help generate the adversary example close to a boundary. So the math is here. Feel free to read through them. And I always encourage people doing AI to read this math. It's actually very simple. It's just the key idea is that minimize the distance to the boundary, minimize the confidence score. So a visualized process is showed here. So step one is that we get the source image and we get the guide image and we have the adversary perturbation. So we extract the features, right? After we extract the features and we start to compute the class salience map, right? To decide what point we need to adjust in order to make the adversary example or the legitimate example close to the boundary. And then we optimize the perturbation and do the optimization again and do this loop from feature extraction to salient feature and to the box constrained BFGS optimization. So this is a process. So eventually, we would generate a set of data for training. So here are 3 different examples. So let's just take a look at the left bottom corner. We have 3 images here. The first image is a genuine image, the source image. So the classification would correctly classify it as the neutral face. And the confidence is 99%, which is very high confidence, right? And we also have another second picture is a guided picture. It's a happy face. And the classifier will tell you that it's 98% of confidence. The third image is the image that we are working on. If you are just trying to develop an adverse example, then we need a third image is based on the neutral face, will be classified as a happy face with very high confidence score. That's a very successful adversary attack. But for our case, we want is it being classified either as correctly as neutral or incorrectly as happy face, but the confidence score is only 1%, very low. Because this image and all the third column on these 3 sets of image is those, I would call them the bad adverse example with very low confidence score, but a very good example for our boundary extraction. Okay, now we prepared everything, so it's the job to do our model stealing attack. Okay, so the approach is that first, we using all the adversary, we using the feature full method to generate all the adversary examples with low confidence. And then we would query the machine learning as a service model in the cloud using this adversary example, and we generated their response. We only need from the cloud, we only need the classification results. And then using this result, we would take a candidate library we call the model zoo. It's an existing machine learning model. And we're using the cloud query result to train our own model. And this become a stealed model. So this is just a high level. Let's take a look at the real example. So what we do is that first, we have 2 sets of data. One is genuine domain data, which is just the not adverse example or not being modified. We also have malicious domain data. These are data being modified very close to the boundary. Will be classified correctly or incorrectly. So why we still need the genuine domain data? Remember that we are targeting the machine learning model on the cloud as a fully black box. We don't even know what kind of label they would provide us. So the genuine domain data is mainly to query the machine learning model service to extract what kind of labels they will provide. And the malicious domain image or the data set will be used to extract the boundary. So you see, in order to extract a fully black box machine learning model, we needed to know what is the functionality of that, what kind of label it will provide, and then what boundary they are. And then all the queried data become a synthetic data set with we call the stolen labels. And then we have our own machine learning model locally. This model have multiple layers Some of the layer are reused layer, which is already fixed. Some of the layer are retrained layer. And normally the retrained layer is at the end of the machine learning models. And then we're using our synthetic data set to train this model, eventually to train the last few layers. In our case, we normally train the last 2 layers, or sometimes 1 layer, a full connected layer. So in that way, we generate a model, and this model would have very similar behavior with the machine learning model in the cloud. Okay, so this is the thing. So for example, using an emotion classification. So what we do is that we first choose a local model, say VGG face. And then we are generating a collect images relevant to the classification problem for the, we call the relevant query. And then we query the machine learning model, and then we train the local model to replace the remote machine learning model. So now, a few questions I guess you may have, so I can answer in front. First, what kind of local model you need to use? The answer is that you can use any local model, which means that in the cloud server, they have a face recognition. Locally, you can use any local model, a car plate recognition model, for example. But if the local model is slightly relevant to the remote model, the performance will be the best. So if you know, I think you kind of have some idea if the overall goal of the remote model, if they are like recognize the face, then the local model you'd better choose something like a face recognition. If the remote model is classified the flower, the local model better is related to flower. This is public information, and that will increase. Again, you can use any other models as the local model, but a relevant model would increase the success rate. Okay, so that's one thing. The second thing people are asking that how can you generate the low confidence malicious state image? Because even though the cloud will provide you the low confidence, the confidence score, we don't use that. But how do you know that? Because you have not extracted the remote model. This is another very interesting example we called adversary example transfer learning. Again, adversary example is one attack. Transfer learning is another attack. These can combine together. So the key idea here is that the boundary in the local model, a similar model, is very similar to the boundary of a remote model, which means that any 2 machine learning model, as far as they are classifying similar image or similar items, their boundary are similar. We are working on, don't worry, don't ask more questions at this moment. We are working on the mathematical proof for that now. No one have proved that. Many people notice that. So now let's take a look at the experimental results. Say we're using the Microsoft service, and we're using their traffic machine learning model and the flower classification model. So you see that we only query a few hundred times, or at most 2,000 times. And the price is only a few like dollars. And we can achieve very high accuracy. In fact, if we query like 2,000 times, which costs us $2 or $7 in the 2 data set, our feature full, the FF means our feature full based extraction attack. CW is CW based feature model extraction attack. Again, our model extraction attack, we can use all existing adversary example generation method. It can achieve 76% accuracy and 88% accuracy, or even 89 using CW. this value is already very close to the original module's accuracy. So we, using 2000 query, we can fully recover that. So if you want to compare our method with the previous method, we eventually, leveraging the another adversary example case, we can extract parameters around 200 million parameter size machine learning deep neural network model with only 3,000 query, and we can get a very high accuracy, and the still cost is very low. So I think I'm running out of time. Just a quick defense. So far, I have to say that in academia, we have developed some defense, but in the machine learning model in the cloud environment, the defense is not there yet. So some of the defense is mostly trying to identify the input. So in our case, we can easily adjust our parameter to evade those detections. So I don't want to go deep in that. I would, because people would argue that it's only one defense. How about other defense? But overall, our claim is that so far the defense did not work. And even worse, for this inefficient defense, the machine learning model in the cloud has not applied them yet. Right? So as a quick conclusion here, that we have proved that different machine learning attacks can be combined to become an even more powerful machine learning attack. So far I have discussed in our work, we combine 3 techniques: model extraction, adversary example, transfer learning. Okay, so if you don't really know these concepts precisely, just check, Google it. So, and these 3 attacks were developed kind of independently for under different threat model. And we prove that this threat model or these attack vectors can be combined together to become even more powerful attacks. So now I hope that, including to my students and myself, we want to understand more of the mathematical background of all this phenomenon. Because so far we are using machine learning model more or less like, okay, it's a black box. I don't know why it's work. As far as it's working, I don't care, right? But it's actually leave a kind of like a big minor for the hackers. So my talk is just one example, and I'm sure that a lot of AI attack example will be coming out, and there will be different combination of different technique. And the funny thing is that for the defender, for the AI developer, they don't know why their method works. So they don't know why the attacker works either. From the attack's perspective, most of attacks are also in blind. We don't know why transfer learning would work or why adversary example would work, but we just combine them together and to make it work even better. Our goal is that, can we explain the situation? Can we explain the mathematical background, why it doesn't work or why it does work? Okay, so, and in the future, we are also very interested in extracting the model from AI chips and AI accelerators, which are embedded in our computer, in our cell phone. And we are using this method, and with the combination of hardware side channel, we have some work trying to measure the EM, electromagnetic emissions, so that we can tell you what happened inside the AI chip, so that we can rebuild the AI chip. Okay, so again, this is a black hat talk, so I'm focusing more on the hacking side. If you are interested, we can work together to come up with stronger defense. Okay, thanks. Thanks for attending my talk. So I think I still have a few minutes for questions. Yeah, thanks for attending my talk. So I'm looking forward to any questions. Yes, actually, I already answered some questions during the presentation. I mean, these questions are great. So one last thing, I think there is one comment, not really the question from Eric, is so it seems very difficult to develop the defense, which are universal, like workable. So the final conclusion we have is actually the opposite way. A lot of attack were universally working on different AI models, but the defense seems quite ad hoc. So there are two very interesting research directions here beyond just developing adversary example. One is how we can mathematically understand that why this attack with the universally working, right? Why this boundary will be similar. Second would be how we can combine all this ad hoc defense together. While I'm talking, I do see a few comments here. So one comment is how can we look into the tripwise for this kind of model extraction attack? It is our work. In fact, we are a bit concerned to perform this task because we know that the chip manufacturing, they spend so much effort in developing AI chips. They want to keep all the secret. And we have no desire to kind of like steal their IP. But we still want to see whether leveraging this kind of like model extraction attack, along with all other, for example, side channel attack, we can extract the internal of this, we call AI accelerators internal structure. And our goal is, as a researcher, our goal is to make them more secure rather than just to hack them. But if we hack something, we will present in black hat. So where can we? Oh, the white paper. You should ask Black Hat because I did submit the white paper to Black Hat. But yes, another folk mentioned the NDSS paper. That paper actually including more technical details. Yeah. Okay, so I guess we need to wait for a couple minutes to see if there are other questions. So, okay, good. So one thing I would encourage people to look into is trying to, I think there are other talk, I glossed over other talks. This afternoon, there is another talk mentioning that how we leverage the adversary example for defense. This is actually a very interesting area. So we know that adversary example is prevalently available in all this design. So now the question becomes how we can leverage it instead of attack the system to protect the system. And also using this for like watermark fingerprinting. I would say these are all very interesting areas. So overall, the key motivation of our work is that we want to help people better understanding the security of AI before we widely use the AI. And AI has been applied in almost all different areas. And the security, I know that the security, as a hackers, we are so happy that people all using different AI so that we can hack in all different systems, like in 1990 or 2000 that we're hacking all the operating system. But I hope that we will not go in the same old route that we develop a lot of system, unsecure system, and we're hacking all of them to ask people to kind of like fix those problems. We hope that we can build security inside. Okay, so again, thanks for attending my talk, and please feel free to send me email if you have any questions. My contact information is on the slides on the white paper, and you can easily search my name and find my web page. We do hire recruiting postdocs, PhD students who are interested in this area. Okay, thanks.